As you may have known, the old brainstormers have graduated, and we asked their team captain, David, to tell us a little bit about how their robot was built in the 2017-18 season. We think this will be helpful for rookie teams and teams with not much experience.
Okay, as far as the structure goes, in the beginning, especially for a robot that has like a pass-through design like this, I had to focus on kind of two individual sides with very minimal structure in between, which meant that the bottom had to be really strong. And usually the easiest way to do that is like an H, which is what all of our past robots have been. And so I then tried to do like an L, which was like a beam here, and then another thick beam down here, but there wasn't enough support in the front. So what I did is I used one of these plates, and alone the plate is not very strong. It's really flexible. But in conjunction with this beam and this beam down here, it gave it a lot of rigidity this way because it's a big plate. But then also either one of these helped give it more support this way, so that when the robot's just sitting there, it doesn't fold in on itself. And then this beam was added later on to sort of help with that as well. The main part of the robot that actually keeps it from sagging in on itself is this beam right here, which is actually just used to keep the two collectors a fixed distance apart, but it also just keeps the robot from sagging in on itself. If you actually look at the back, there's a certain amount of leeway that you can have in building the robot, so the back can actually flex inwards, which isn't great, but it was good enough for how light the robot is. Also, the fact that the lift comes up and kind of gives it that support also helps with the structural integrity. Having two channels on either side is really useful because you can mount the motors and the wheels in such a fashion that you kind of have a unit that is all drive and chassis and structure, and you can worry about everything else just kind of being put on top of that. So one really important thing about building the chassis is that when you're connecting the wheels together, you want a really robust system. So if you take our robot and try to move these around, there's a little bit of play, which isn't optimal. Down here, there's a lot less. Basically, when you're building this small drive assembly right here, you want to be careful about making sure that everything's pushed together properly and there's spacers in places if stuff needs to be opened up. That way that this thing won't jiggle around, and that can also lead to some pressure. But just like in LEGO League, if you had an axle that's supported right here and you have your wheel all the way out here, this is going to be able to bend. Now this is steel versus a plastic rod, but it still does bend under the forces of the robot. So the closer that you can get the point of contact of the wheel to the next point of contact to the chassis is the closest that you can get that, the least amount of flexing there's going to be. And the best way to do that is to actually have your wheel here and two guards on either side and it evenly distributed. But that's often really hard if you want your chassis to be as wide as possible for the most stability. So this is the closest we've gotten, where you just have 2 points on either side of the bracket right here, and then you have sort of 2 points of structure on the inside of the wheel as well, because it's connected over here, but then it's also supported on the other side, and that just keeps the wheel from flexing, and it keeps it from flexing with respect to the channel itself. And then it's driven on the other side so that you don't have to worry about the drive gear adding any flex to the rest of the system. So generally to build structure that goes up, you have a whole bunch of flat pieces or pieces that mount onto the top of the beams. So in the back here, the lift is just literally just screwed straight into the beams. So if you look down here, you can sort of see these 4 screws. It's just screwed straight into the beam here. So that's one way to mount stuff. And then another way, which is how the collector is made. If you look inside here, there's this flat, kind of like a beam piece. That's a thinner piece of aluminum that kind of just goes up, and that's what all the collector is connected to. So it's fastened in one point there, and then there's also a beam that kind of goes from down here across and attaches down onto the top of that beam, and so that's how the collector is really mounted, and then one beam that goes across here. Most important thing about a cascading lift or any sort of stage lift is that you often have these, long bars or extrusions or something like that that will all end up like this, stacked on top of each other in some sort of way up, and that's how you get, some object down here all the way up to up here. But they obviously have to slide inside of each other, and so your slide itself, so say this is your slide, it's going to be attached to one thing and sliding on another thing. So in this case, it's going to be attached to here. We're just going to make that line thicker, and then it's going to slide up. But the problem is, if this is all you had for your two slides, here, I'll draw a picture of just two right here. So say your slide is attached like that, and it's sliding against this one, and it's attached to this one. If you only had this, if there's any pressure over here that could pull your slides apart, and whatever the slot is that it's sliding in, that would add a lot of friction. And so having another slide up here that's attached to this one and sliding against this one, these two will slide up each other. This one will stay fixed, this one will move up, and then they'll butt up against each other right here. And what that does is it provides support all the way up as it's sliding up, so that even if there's pressure this way, this is holding on to that, and so there's going to be even friction distributed between the two, and that does a lot to make sure that your slide can move up smoothly. And so if you look at the robot over here, on the extension out, that's what you see. There's a slide right here that's attached to this piece, and there's a slide right here that's attached to this piece. So as it extends out, this one's supporting right there, this one's supporting right here, and so even if there's a lot of pressure here or out this way, that pressure isn't being put on one point, it's being put on two, and so that really distributes it to make sure that it can move smoothly in and out. The lift on the back is a slightly different type. So this one, it doesn't have these big bars that are moving up and down. It just has one stage, since this only had to move 12 inches up for the two cubes. Basically, there's this little roller system down here, and because there's one on either side, and because there isn't this big bar to add leverage to torque this around, this is good enough to just be lifted up and down. Even if you look at it, it's not just one set of wheels, it's two sets of wheels, for the same reason that there's two linear slides on either one of these, just to add strength, and so if there's any torque put on the system, it can still slide really smoothly. So the way that a normal strung lift works is there's a spool down here, and your string goes up to the first stage. This is the one that's attached to your chassis, and then it comes around to the bottom of this one, and then it goes up to the top of it, and then down to the top of it, to the bottom of this one. This not important. So basically what this does is, as this pulls, it's pulling the string all the way through here, and since these are both heavy, these aren't going to move yet. And so what this will do is, since the string is being pulled down, it'll pull this string up, so this one will move up before any of the other ones. And then once this gets stopped at the top, then that string is going to be pulling down here, and since this is going to be all stuck up, this will basically be another anchor point, and so it's just going to be pulling that up. And so then you can just stack that on top of each other over and over and over again, like we've done on the side extension, and that'll basically just make something that'll keep on extending out. So you can kind of see that pattern. So this is our pulling spool, and so it comes over here, over and over and over and over, and just keeps on going around until it gets to the final one, which is right here. You pull this, it's pulling this string, which is all the way down here, and it's slowly just pulling all of them. Because this is sideways, it doesn't follow the same rules that I was explaining over there. But to see, the first one is going because this spool right here is pulling right here, and then once it gets all the way up to there, it'll start pulling this one, and so on and so forth. And then when it gets to the end, it'll just stop. And for the pullback, the way that this stringing works, basically every little bit that you pull this way is the same bit that gets pushed out, because there's a certain circumference, you pull that amount of string in, that's the distance that it's going to go out. So what you can do is we've just directly connected this last stage to this spool, so it's pulled back here, just so that it's pulling straight back. So the string comes back here. It looks really complicated here just because it needed some extra anchor points, but it comes around this spool and then comes back to here. So as this is extending out, this spool is just letting go. And then when we want to pull back, this spool pulls in and this one lets go and all the string comes back. So it looks really complicated, but it's kind of simple in that one is pulling out when you're extending out and one is pulling in when you're extending in, and vice versa for the other spool, so that they're kind of just doing this and counteracting each other. One thing to keep in mind about motors is sometimes it's useful to use a different gear ratio for the motor and then do your gearing externally. So if you look at our robot, I'm pretty sure there's only like 1 or 2 places where we use only the gearbox and no gearing. So for every single drive motor, we use Neverest 40s, right here, right here, right here, right here, and then we gear them down 2 to 1. So it's actually technically inefficient because the motor's moving really, really fast. Then inside the gearbox, you're gearing it down to 1 to 40 or 40 to 1, and then we're gearing it up to 1 to 2. So we're making it slower than faster, which is really inefficient because you're adding friction or whatever. But the Neverest 40 gearboxes are a lot stronger than the Neverest 20 ones, so that's why we use those in this instance. Also, because there are Neverest 20 gearboxes that are stronger, but they're not an offset shaft, so you can't adjust the tension. And so that's really useful as well. So that's why we chose to do this system. Even though it looks kind of inefficient, there are advantages to doing that kind of system. As far as our collection, we have Neverest 20s in here, and then we gear them down because we don't need as much speed. And also this kind of gearing just fits better among the structure that we have around it, because there's these posts here and there's wires that have to go through. And so these larger gears were actually more useful because we had more space to put stuff through them. Another important thing is that more often than not, doing chains is just better than gearing, because the teeth are really small for safety reasons, and that means that they can easily rub up against each other and cause problems, whereas the chains, it's really hard for them to skip, and they're also just more consistent in terms of not wearing down. So the one place that we did use gears was a relatively low stress point, because we have a pretty low torque servo here against here, and it's just only torque rotationally. There's no forces pushing in and out or out on these. This is a good option for the gears because it's not high stress, but for something like a drivetrain, you have to make sure that those gears are really, really well attached, really, really well supported on either side, or else they could flex out and skip. The other 2 motors are relatively simple in how they're supported. They're just kind of connected directly to the axle. Like they don't have any gearing, so this is an Neverest 20. It's just going straight up to the spool. It's supported in 2 places here, which is really good because the axle doesn't put a lot of pressure on the motor, which maintains the gearbox's longevity. And then this one down here is also just connected directly to the motor. So this is probably the simplest that you can see the motor here. It's kind of covered up right here. And this is nice because this lift is heavy, but there's not a lot of stress on it because we're doing this pulley system. It's just a lot simpler to put it together like this, because if there's anything wrong, we can just swap it out really fast. As far as servos go, there's all kinds of different servos. Some have plastic gears, some have metal gear, some have aluminum gear, some have steel gear, and for every single different one, you have to use them differently. So starting at the steel gear servos, which are the strongest, you really can use them in any scenario that you want because they're steel and they're so strong. So these ones right here, we're just mounting directly to the servo itself, and there's a lot of stress on this system because we smash into the walls with this extended out, and the steel gears can manage all of that. And so one important thing to note with higher torque servos, you want to use 4, or stronger servos, you want to use 4 screws all the way around, because you can be lazy about that with lower torque servos like these ones. But these ones, it's really important to make sure they're secured down, because all of that force has to go somewhere, and it often goes to the plastic case of the servo instead of the actual inner workings of the servo because they're stronger than the plastic case themselves. And so making sure that that's fastened down nice and neatly is important. Another way to use it is using a servo block, which is probably the best way. And if you can fit it in, it's the best practice because this is the strongest way you can possibly mount a servo. Basically, there's a connection right here to the servo, and there's another big bearing right here. And this big bearing in here takes up all the force, so I can take this and wiggle this around and do whatever I want. And there's very little strain that's going on the servo teeth of the actual servo. And this is a steel gear, so I could have mounted it just normally, but like I said, it's good practice to use a servo block. Moving to aluminum servos, we have one down here. We are mounting it just directly to the servo itself because it is fairly strong. It is metal versus plastic, and so this one is just a winch for the poker. And because this is a pull and push situation, and there's a lot of torque in this little pulley system, it didn't really matter to be mounted with a servo block, and we didn't really have the space for it. But with aluminum, you can just mount directly to the servo, as long as, and there isn't a ton of stress on this. Like it's nothing like this beam right here. It's just rotational, so this is pretty safe. This over here, this is another aluminum servo, which is pulling off the relic. This right here, there's tons of stress on this system, so it was a little bit more important to protect this servo. So that's why we have a gearing right here, also enough so it has enough torque to lift this whole assembly. But this little gearing right here, obviously any torque that goes on with this shaft has nothing to do with this servo because there's gears in between. They're not even the same part. So because of that, I can move this all around and it doesn't push at all on the servo at all, and it's protected because of this gearing. Plastic servos like this one, we're using a servo block. That's the best way to protect the plastic gear servos. Down here, these have a lot of torque against them if we run into another robot. So we are using the servo blocks, and it doesn't put any strain on the servo. Another scenario that we're using servo blocks is down here with the dual mechanism. There's a servo block stacked on top of a servo block to get a lot of range of movement. So this is like a 2-axis gimbal. So this servo block's mounted on top of this one, and then this one's mounted onto the arm. And that is a really nice thing about the servo blocks. They are kind of bulky and chunky because they take up more space than just the servo directly attached to whatever arm or gear, but they are really easy to mount because there's mounting surfaces on every single side. So these ones are put on the side, these ones can be put on top, and so on. For sensors, the most important thing is for these optical sensors, they're mounted on 2 sides. We did have a mount here that supported the other side. I don't know where it went, but supporting on either side is really crucial, and making sure that there isn't any stuff in the viewfinder. So this one kind of comes out like a column and there's nothing in the way. It might look like it, there's nothing in the way. So you can get good readings. On this robot, it's used to detect when a cube is coming through or when the cube is at a different orientation so that we can correct the angle of the cube as it comes into the robot. As far as distancing this from the ground, closer is normally better. Obviously touching is really bad, but the closer you get, the higher resolution you get. So these sensors are fairly close to the ground. So there's little lights under there that are shining on whatever color is there. And so if it's really high up, a lot of that light is dissipated to the surrounding area. But the lower it is, the more concentrated it is, and the higher the light reading is that you get. If you actually put the camera over here, you can see the sensor really well and how high it is off of the ground. So it's about, say, a centimeter off the ground. And that was a really sweet spot for the light, but closer would probably work. Further out also works, but you get readings like red is 3 on the gray and then 5 or 6 on the red. So that's not as useful because then if there's any noise, then that's bad. But the closer it is, we're getting like 10 on the gray now, and then like 60 on the red, which is much nicer because then the numbers that you use don't matter as much, and you don't have to have it as well calibrated for the lighting conditions. For the encoders, these are really annoying, and I would suggest using different ones. But if you are going to use them, it's really important to follow the directions in putting them together. There's like a little tool to slot the optical disc on top of the board that has the optical sensor to read the rotation. But making sure that your cable is strain relieved and that this is not going to be hit by anything and that your shaft isn't going to move up and down is really important to make sure that the optical sensor works inside of here, because the way it works is there's a little sensor and there's basically a clear disc that has a whole bunch of tick marks on it, and so we can optically see how many tick marks have gone by, and that's a really accurate system because there's so many tick marks that you have really good resolution. But that does mean that if your disc moves up and down in distance to the sensor, that can throw off your reading. So if it's touching, it doesn't read anything at all. If it's too far away, it doesn't read anything at all. So there's that little sweet spot, and that's why there's a tool that can be used to put the disc down on top of the sensor. But that disc is attached to the axle and not anywhere else in the sensor. And so if this axle moves up and down at all, then that means that the disc is changing its distance from the optical sensor, which can change your readings and change the accuracy. So making sure that this rod can't move around, we made sure that can't happen, so I can't really show you. But if you grabbed the wheel and jiggled around, that would be bad, because that means that the shaft is moving up and down, and that means that your disc is moving up and down as well. So as far as limit switches go, kind of like touch sensors, just a little bit more bare bones. So this is an example of one. The ones that we use, they have 2 holes and they line up with the holing pattern of these randomly. So that's how I mount them. The wiring is you have to attach one to a middle prong. So I think the middle one is ground. No, the middle one is signal, and then the other one is ground. You have to look at the wiring diagrams. But signal and ground, no power, because if you add power in, that sends power back into the board, and that's really bad. So for the Rev Robotics system, you want to use just the signal and the ground. And when you're having stuff hit it, you want it to hit this part right here. That's the whole point. It's a little lever to hit the actual touch sensor in there. It's really easy to press this down, and that's the whole point, is that you don't need a ton of pressure to press these. And the way that this system is working is it's actually like a pass limit switch. So this one moves past it and actually rubs against the top. So you can see right here it's passing over it, and now it's pressing down. And then when it comes all the way back, it lifts back up. So that's another place that we're using the limit switch. We're using it at the top as well, except this is an actual touch sensor from Rev Robotics. So this one's the top, and it's actually the physical stop as well, which isn't the greatest practice. You want to make your physical stop and your touch sensor stop different, because you don't want all that force going into the sensor, because the sensors are often more expensive than some physical thing on the robot. So over the season, the changes that get made are really similar to the way that you guys would change your attachments in First LEGO League. Sometimes you have to make a large change that will, you have to take apart the entire attachment to make it better in some way, maybe change the structure, or the attachment work better by just scrapping it and trying a completely new idea. And so, for example, we had a slightly different relic design in the beginning, and it was kind of rotating and stuff, but the way that the robot's designed is this entire relic system can come off with like 4 screws, just right here, and this entire system comes off. And so that was one big change that I made. There's tons and tons of tiny ones, like for example, this is just a little switch guard. Little things like that you can just slap on. So later on in the season, we realized that having an extended collector was better at breaking up the cubes for autonomous collection. And so, originally we just had these motors right here, and I had to find a way to add these in somehow. the way that the robot was built is, the only structure for this collection is this beam up here, which made it actually pretty easy because these could just rotate around the wheels that we have right here. And so basically I just built the system initially, and it didn't actually retract and come in, and it was just fixed. And then from that I tried to make it so it could retract in and out, and I got rid of all of the assembly here that was prohibiting it from doing that. And then I made the assembly that could actuate it in. We have a video posted about wiring, so that's a really important thing to watch. But generally, you want to keep everything as insulated as possible. And so, as far as wiring goes, just make sure that you're using this cable sleeve all over the place as much as you possibly can, because it just helps isolate things, and it can keep things very organized. It can also make things really messy, so you have to be really careful about how you organize it, because it does make the wires fatter. Also, using tons and tons of zip ties and constantly strainer relieving things, because if there's anything moving inside the robot, it gets caught on like a power cable, and you yank that power cable out, then you lose functionality of your robot. So keeping everything as plastered to the frame as possible is really important. But again, because it's plastered to the frame, you want to make sure that it's not touching the frame.